Hi and welcome to this video. We will talk about the file format of Parquet, and we will look into the context of Apache Spark as what are the different configurations we can tune to work with it efficiently. In this video, we will learn that Parquet with Apache Spark is popular and both of these have been evolving. There are a lot of opportunities so that we can make the most out of it. A lot of optimizations are there inbuilt by default, which includes predicate pushdown, column pruning, dictionary filtering, column indexes. And on top of these, there are other configurations which we can tune to work with it efficiently. Like we can choose a different compression codec, we can push down aggregates, we can enable Bloom filters, and we can also control the sizes of the dictionary, size of page, size of row groups, as well as the size of the batch for vectorized reading. There are two layouts of data. One is the row oriented, where you have all the attributes or all the column values of a record stored one after the other contiguously. So in case you have got 4 records with 3 columns, this is how the layout will look like. A lot of OLTP databases like MySQL and Postgres implement this kind of layout, and file formats like CSV, JSON, XML, and binary encoded file formats like Protocol Buffer, Thrift, and Avro also have a similar strategy. The benefit in databases is that you get all the attributes of a record, like you get all the attributes of an entity like a user or an item, and you can also perform updates on top of it. There can also be indexes in databases to efficiently search for an entity or a range of entities. The other layout is the column oriented, in which all the column values across all the records are stored one after the other contiguously. So in the same setup, when you have 3 columns with 4 rows, this is how the layout will look like. Databases which perform analytical queries like BigQuery, Redshift, Vertica have this kind of a strategy, and file formats like RC, record columnar, or ORC, which is the optimized version of RC, and Parquet fall into this bucket. Now let's look at some of the human readable file formats which are row oriented or record oriented, like CSV. We have XML and JSON as well. These file formats are quite popular in a lot of context, but they have their own demerits. For CSV, you actually don't know what the column is, what the name of the column is, unless you have a header. And a lot of times when the schema changes, you will have to manually intervene into the code to make it work. There is no differentiation between numbers and strings if the string has only digits, and you have to manually choose what should be the delimiter and what should be the escape characters, because if your delimiter is comma and your column value also contains comma, then you will have to escape them. And there is no standard way to represent complex fields, like your data can have list arrays, it can have map of key value pairs, it can have nested fields. So it becomes quite hacky and cumbersome to represent those kinds of structures. In XML, there is support for a schema, but usually it is very complex. And because of the repetition of the field names in the form of the tags, it becomes less space efficient. Again, there is no differentiation between the numbers and strings if the string has only digits, and there is no support for binary data. Let's say you want to represent unstructured data like image. There is a way to convert into base 64 encoded string, but that again increases the size by at least a factor of 33%. JSON is also quite popular, and it supports a schema, but a lot of parsers and tools don't implement it. And a flaw with JSON is that if you have integers which are more than 2 raised to the power 53, because of the way numbers are represented, you cannot accurately represent those integer values. There is a repetition of field names with each record, making it less space efficient, and there is again no support for binary data, just like XML. But if you see our analytical use cases, they are much more suited for column based access, where a lot of queries access just a few columns out of dozens or hundreds of columns in a fact data set for filtering operation or aggregation or join operations. So there you won't like to parse, basically scan through all the rows and parse just a handful of columns. Rather, if columns are stored together, you can directly go to the specific columns and fetch their values and avoid scanning the columns you don't need. This also benefits with vectorized execution, where you can load all the column values into a CPU cache and perform a tight loop across the values for your operation. And once you store all the column values together, that also leads to an efficient storage and processing, because we have multiple ways to compress the data, as we will shortly see that. So what we need for analytical use cases is binary encoded data, which supports schema and is friendly in analytical access. So a lot of strategies which is used to encode the data includes bit packing, and then there are a lot of other strategies. We will look into it. What happens in bit packing is, let's say you have an integer between 0 to 100. We are representing age, for example. Now, in a lot of programming languages, integers are represented as 4 bytes, but do we really need 4 bytes for this range of integer values? Maybe 1 byte is sufficient for such a range of the value. And if you choose to have 1 byte for this range of values, for 100 such values, we will need 100 bytes. But we can be a bit more optimal over here. And what about using just 7 bits for representing the number between, representing the integer between 0 to 100? And for 100 values, we will have to use only 700 bits, which translates into 88 bytes. And we will have one more byte just to represent what is the bit width, which happens to be 7, like 7 bits to represent this integer. So we can be more compact in the space requirement. And this strategy is called bit packing, where you pack together only the required number of bits one after the other and parse it based on the width of the bit you are using to represent the integer value. Similarly, there is variable length, a concept of variable length integer, where you don't upfront tell how many bytes we will be using for encoding the integer value, because different integers can require different bytes to represent it. So what happens in variable length integer is, one of the bits, the most significant bit, is set to 0 or 1. 0 means the value will continue and then the next byte has to be read, and 1 means the value has now terminated in this byte, which means you can now go into multiple of 1 byte, and different integers can be encoded into different number of bytes based on their actual value. And one more thing to note over here is, variable length integer can be signed and unsigned if it is, and based on that there could be different overhead of the bits. If it is unsigned, you just have 1 bit of overhead just to represent whether the byte is going to continue or not. The other technique which is commonly used in columnar file formats or columnar databases is the dictionary encoding. Let's say you have a field, a column, which contains the operating system over which certain event happened. This is a desktop operating system. And now if you have, let's say, Windows, Mac OS, and so on, these column values one after the other, in the naive layout, it will take 39 bytes, assuming each character is taking 1 byte. We can optimize this structure by using a dictionary which has an integer index and a value. So this applies to the columns which have low cardinality, where the number of unique values is less and they can fit into a dictionary. The values go to become the actual value of the dictionary, and we assign one integer index. For example, Windows can be assigned an integer index of 0. Mac OS can be assigned integer index of 1 and so on. And now in the actual data, instead of storing the actual content, we can store just the indices. Like instead of Windows, we use 0, instead of Mac OS, we use 1 and so on. With this layout, as you can see, if the integers can fit into 1 byte, we need just 7 bytes because there are 7 integer values, and then there is a size of dictionary. In this case, it happens to be 20 bytes. So what was represented in 39 bytes can be represented in 27 bytes. However, this was the case with where we had just 7 values, but think of a situation where these 3 values or a finite small number of values are getting repeated a lot of times. Then the size of the dictionary basically amortizes and becomes less significant, and the space savings is even higher. Now, coming to a situation where you have a single value getting repeated a lot of times. For example, think of booleans. If you represent booleans with 0 as false and 1 as true, then in a lot of programming languages, there is 1 byte given to the Boolean value. It will require 128 bytes to represent 128 Boolean values. With bit packing, we can be optimal and we can use just 128 bits because Booleans can be represented as bits. 0 means false and 1 means true. So it will require 16 bytes. However, it can be made even more optimal because you see all the 0 value is getting repeated a lot of times. In this example, it is getting repeated 128 times. So why don't we store just the length, the run length, like how many times it is getting repeated, and the value which is getting repeated. By doing this, if we encode the length as 1 byte and the actual value also as 1 byte, all we can do is make just 2 bytes to represent all these 128 zeros. So that's even a stronger space benefit. And this run length encoding is also used in multiple places, like compressing your black and white images, where you have black and white pixels and a long series of repetition of either black or white. They can be smartly encoded with a run length encoding. If the column values happen to be changing, but not much within a range, we can make use of delta encoding. Think of timestamps. In Parquet file format and in many other systems, timestamps are internally represented as integers. For example, if your timestamp is in milliseconds, you can use 8 bytes of integer to encode them as epoch. So let's see, we have 6 integer values over here which are representing the timestamps, and over here the difference of the timestamps is not huge. So instead of using 48 bytes for 6 values, what we can do is we can store the minimum value followed by the difference of the actual value from the minimum, and those difference will be small integers. So over here the first value can be of 8 bytes, whereas the subsequent 5 values will be 1 byte each. So overall we can represent or encode the same data with 13 bytes instead of 48. In strings also, similar technique can be applied. If you have string values where a lot of prefix is in common, then instead of storing the actual string value, which in this case will take 34 bytes, assuming each character is 1 byte, what we can do is we can store the prefix and the length of the prefix and the suffix only with the instead of the actual value. So the way it looks is, for the first value George, we say the prefix length is 0, which means it does not require any prefix, it does not depend on any prefix, and the actual suffix or the actual value is George. But for the second value, which in this case happens to be George second, we can specify that, hey, it takes 6 characters of the last value, which happens to be George, and it appends or uses the suffix of space and 2. Similarly, for the third value, we say that it takes 9 characters from the previous and it adds a suffix of 1 on top of it. Similarly, for George IV, it takes certain length of the prefix and then it adds or appends a suffix on top of it. So by going through all the values in sequence, we will be able to regenerate the actual value which was in the data. So by doing this, we will be able to encode instead of 34 bytes into just 15 bytes. So all these optimizations are possible if your data is stored in a column oriented layout, because all the column values will be one after the other, which means their data types is going to be the same, and that also gives us opportunity to make use of optimizations when it comes to storing those data. And again, the optimization also happens when you try to process the data. You can smartly select which columns to process, and you can make use of vectorization as well. Coming back to Parquet, the root of Parquet is in Dremel, which was a paper published in 2010. This paper talks about a schema of a web document, and in that web document you have different fields. Some fields are required, which are mandatory, some fields are optional. There could be fields which are repeated, think of it like a list or an array of values, and then there can be nested fields as well. For example, every document has a unique doc ID, and then it has got links, which is the backward and forward links of the other documents. Again, this backward and forward is a nested field inside links. And then you can have repeated fields like list, for example, name, which in turn can have another repeated field of language and optional field of URL, because every document can have multiple URLs and multiple country and code combination. And in the paper, they also talk about a couple of schemas on which they build up the concept. Parquet is heavily influenced by Dremel, and what happens in Parquet is it is essentially a hybrid where rows or records are divided into horizontal subsets, and then they are encoded with column oriented layout. But to begin with, Parquet is quite popular, at least in the Spark community. And a lot of table formats like Delta Lake and Hoodie and Iceberg, they are built on top of Parquet. What happens in Parquet is, like, let's say if you have a file which has got 8 records, first of all, they will be split into horizontal subsets, non-overlapping subsets. And each of these groups of rows are called row groups. And for each row group, all the column values will be stored together. And when storing the column values, it can happen that certain column value will go into one page and the other column values for the same column can go into different pages. So the page happens to be the smallest level of information which is stored in the Parquet file format. But this is the high level idea of how the row groups and column layout look like in Parquet. Now, going into a bit more detail, every Parquet file format has got a header which contains a 4-byte magic number, and then it has got row groups, which are essentially the groups of the records. There could be multiple row groups, and finally there is a footer which contains the schema, and it also contains the statistics of every column across every row group, like what is the min value of every column, what's the max value, how many number of records are there. And for each row group, it is divided into column chunks. So the number of column chunks equals the number of columns the record has. And within each column chunk, it is further divided into pages. Again, there can be multiple pages. The size of the page is 1 megabytes by default. The size of row group happens to be 128 megabytes by default. Now, again, going a bit more inside, every page has got the actual values, but every page starts with a header. Which tells like what kind of page it is. Is it a dictionary page or is it a data page, followed by the repetition and definition levels, and finally it has got the encoded values. There are a lot of configurations which can be applied, like what should be the size of the page. By default, it is 1 megabytes, but you can choose it. Whether you want to enable dictionary encoding or not. If yes, what should be the size of the dictionary? The size of the dictionary is also 1 megabytes by default. So if all of your unique values can fit into 1 megabytes, then it uses dictionary encoding for that column in that row group. And again, same column can be dictionary encoded into in one row group, and the same column may not be dictionary encoded into the other row group. It all depends on how many unique values are there, or what is the cardinality of the column inside every row group. And because this page happens to be the smallest level of information which is stored in the Parquet file format, you can apply compression as well on top of the pages. And then there are a bunch of compression algorithms supported by Parquet. In Spark, Snappy happens to be the default, but then there are a lot of other compression algorithms as well. We will see that as we go ahead. You can also choose to not do compression at all. That is also a possibility. If you happen to go through the Parquet documentation, you can see an image something like this, which is similar to what we have just discussed, because a file is a container of header, the actual row groups and footer. But on top of it, you can also enable Bloom filters. Bloom filters are probabilistic data structures which tell you whether a certain entry is absent or not, and it can give you an indication whether an entry may be present or not in a row group. So we can have Bloom filter across all the columns, but we can also choose that on which columns we want Bloom filter. It's not mandatory to have Bloom filter for every column. And the size of the Bloom filter is 1 megabytes. The Bloom filter is there for all. So there is one Bloom filter for every row group. And in fact, for every column and every row group, there is a Bloom filter, and the size of Bloom filter is 1 megabytes. So if you happen to have a file which has got 3 row groups, and if you apply a Bloom filter on one column, your Bloom filter will be 3 megabytes, 1 megabyte for each row group. And if you have a Bloom filter on multiple columns, then the size of the Bloom filter will change accordingly. However, this Bloom filter is not enabled by default. So whenever you are writing a Parquet file, you can enable it. And when you enable the Bloom filter, you can specify what is the expected number of distinct values in that column. Based on that, the representation of Bloom filter will be chosen by Parquet. However, you can also say that, hey, I don't know how many distinct values are there, but you can tell what should be the maximum bytes for the Bloom filter. This maximum bytes has to be a power of 2. So you can say like, okay, 1 megabytes, 2 megabytes, and so on, or 4 megabytes and so on. If you specify a maximum bytes, which is, let's say 10 megabytes, then the Parquet will choose the next highest power of 2, which happens to be 16 megabytes. And then you can tell that my Bloom filter is adaptive, where you don't specify the number of distinct values. All you tell is this has to be the maximum bytes, and the representation of the Bloom filter will adapt according to the maximum bytes you specify. And in the process, you can also specify what is the false positive you would like to tolerate, because Bloom filters are probabilistic. When they say some value is present in a row group, that does not necessarily mean that the value will be present. All it can tell you that the value may be present. However, the Bloom filter is very accurate when it says like the value is not present, then the value is not present at all. So the Bloom filter can have false positives. the default value of false positive is 1%, which is 0.01, but you can control that as well. Higher, if you choose a lower value of false positive, then your size of bloom filter will you will need to have a bigger size for the bloom filter. There is a formula as well, like how many hash functions should be used, and what is the false positive and tolerated, how many distinct values are there. But overall, the thing is, lower the false positive you intend, higher the size of the bloom filter is required. And then there is a column index and offset index as well, which is stored near the footer. What column index does is, for every page, it stores the statistics, like what is the min, max, and count for every page. So you have a statistics not only at the row group level, but also at the page level. Now, we are going to talk about some tests which we performed in order to see how well different configurations behave and how can we tune them. For the test, we took 100 million records with 2 fields. One of the field was user ID, which was integer value, and this was almost unique. We had more than 99 million unique user IDs, and the other field was country, which was a string, and the cardinality of country field was low. There were around 200, there were less than 250 distinct values of the country. We took a CSV file and compressed it in Parquet file format. So ultimately we had 2 files where each file was about 280 megabytes of size. When running Spark, we did that locally with PySpark, giving driver 4 GB of memory, and whenever read was involved from S3, we used S3A scheme because it provides a skippable interface. So the benefit of Parquet is, like, you can skip certain row groups and you can avoid scanning data if your data is, if you know that this row group does not contain the data we want, or if you want to read specific columns only, then you would like to read only that column chunk and not the other column chunk. So you need a way to go to a specific offset in the file and start consuming data from there. And this is what S3A scheme supports. One more thing, there is a Parquet CLI tool which helps you inspect the format of the Parquet, the metadata, the records inside it, and all the other interesting information. You can install it directly using brew install Parquet CLI if you are on Mac. And this has got a bunch of interesting commands, like to view the metadata of Parquet, to view the page summaries, to view the dictionary of a column in the Parquet file, inspecting the schema, looking into some sample records, inspecting the bloom filter to see whether a certain value is can be present or not, and scanning through all the Parquet file. So it has got a really, it has got a good number of interesting commands which you can use. So in our case, when we do a Parquet meta on the Parquet file, this is how the output looks like. You see there is a schema of the Parquet file, which contains the integer user ID and the binary country. Strings are represented as binary internally in Parquet, just like timestamps are internally represented as integers. And over here we have got 3 row groups, as you can see. And for each row group, you see the metadata, like statistics, like what is the number of records in that row group. For example, here, the first row group has got 22.7 million records. The second row group also has the same number of records. And the third row group is a bit smaller, and it has lesser records. And this is because, let's say if you have got a file which has 280 megabytes of size, and your row group happens to be 128 megabytes, then the first 2 row groups will be 128 megabytes, whereas the third row group will be less than 128 megabytes. And that is why the third row group over here has got a smaller count. And you will also be able to see that the start offset of the first row group is 4, because as you remember, the header takes 4 bytes. So the first row group starts at offset 4. And what is the size of the row group before and after compression? Moving ahead, you will also see that for each row group and every column, for example, the user ID column in the first row group has got this minimum and maximum values, and similarly for country column in the first row group has got this range of minimum and maximum values. So all these statistics are stored in the footer, and you can inspect that using Parquet CLI tool. And one more thing about the row group is, because the pages, you can choose a compression of the page, and different columns can be encoded using different strategies depending upon the values of the column and depending upon the data type of the column. So you would also be able to see that there is encoding. So the Z stands for Z standard compression. We will discuss that later. And over here you see the country field, which has got less cardinality, is run length dictionary encoded, whereas the user ID, it is plain encoded. It is not encoded using any techniques. It's just plain values are stored. In Spark, whenever you have to read or write Parquet, it is very similar to reading or writing any other format. If you have to read a Parquet file, all you have to do is get the data frame reader using Spark session. Provide any custom options and just call the Parquet method, provide the path to the directory or to the file which you want to read. And the other similar way to do that is you can specify a format where you can tell that I'm going to read Parquet format and call the load method. If you want to write Parquet files in Spark, all you have to do is get the data frame writer by calling write on data frame. You can also choose what kind of mode you want, whether you want to append or overwrite, specify data frame writer options specific to the file format, and call Parquet method and save the data to a certain location. And other technique is where you can provide format and pass Parquet as the format and call the save method on the data frame writer to save it as the Parquet file format. Now, coming to the optimizations which are available by default, a lot of these optimizations are because of the way data is laid out in the Parquet file format, and because of the way there are statistics stored for every column, for every row group, and also the statistics are at the page level as well. But in Spark, since version 1.2, there was a support for predicate pushdown. So we will look into all these configurations in the context of Spark, but a lot of these apply to the native Parquet as well. And it is a possibility that you will be able to benefit from the Parquet file format in a very similar way in other systems as well, not only Spark. So what happens in predicate pushdown is, as you remember, the footer contains the statistics like for each column and in each row group, what is the minimum and maximum value. So whenever you are trying to read data and you have a filter condition, then just by looking into the statistics of the row group, for that column, you can discard reading that row group altogether if the value which you are trying to search for is not within the min and max range of the statistics of that column in that row group. So let's take an example. We are trying to read for we are trying to filter for a certain user ID. In the physical plan, you can see that this filter has been pushed down to the storage. And once we actually run this, we see that 130 megabytes of data was read. You remember that we had two files and overall the size was 560 megabytes, but we are not scanning all the files based on their statistics, because this user ID was present in the min-max range of only one row group. So only one row group was scanned. And if we look into the execution plan from the Spark UI, we will be able to see that there were two files read, but overall only 22.7 million records were materialized, and in this case the job took 13 seconds of time. Now the problem over here is, if somehow the value which you are trying to look for happens to be in the min and max range of all the row groups, then you cannot discard reading any row group. You will have to scan all the row groups. And this is one of the values which happens to be present across multiple row groups. How did I know that? I just scanned the metadata of the row groups and intentionally choose this user ID. So the situation is, if your value of a column happens to be present in the min-max range of multiple row groups, then you will have to read all those row groups. And in this situation, this value was present across all the row groups in their min and max range. So here we end up reading all the 560 megabytes of data, and Spark had to materialize 100 million records, which is the full all the records of the file. The job took 25 seconds, close to double of the previous setup. And this materialization in the Spark happens because whenever the Spark reads from a certain source, it has to construct rows into its internal row format. So what we will be looking ahead is, how can we save our job runtime? How can we save reduce the number of records which are get materialized, and how can we reduce the number of bytes which are scanned in the actual file itself? One of the configurations which was introduced in Spark version 2 was vectorized scan. Well, this does not reduce the amount of scan, but what it does is it tries to read multiple values of a column at one time. So this is the structure we discussed in the beginning. So looking at the top, for every page, it has got values. So instead of reading and decoding one column value at a time, now because the column values are stored contiguously, why not take a batch of column values, some number of column values, and process them together, which is the vectorized reading. And this is what happens in vectorized scan. So there are a few configurations which you can tune. First of all, you can enable vectorized reader. By the way, it is enabled by default. And then you can choose what should be the size of the batch, which means how many column values you would like to read in a batch. By default, it is 4096, but you can increase and decrease that. Remember, it will have its memory footprint as well. So choosing a very high value may give you may hit memory limitations, in which case you will have to assign more memory to your Spark executor. And in the recent releases of Spark in version 3.x, I guess 3.3, you can have vectorized reading on nested columns as well. So just to look at the impact, first of all, we continue the same example where we were trying to look for a value or look for a column value which happens to be present in multiple row groups, in fact, all the row groups, and we enable the vectorized reader. The amount of data scanned does not change. It happens to do a full scan of both the files. However, if you see, the number of materialized rows also don't change, but the runtime reduces from 25 seconds to 5 seconds. And over here, you can also see that the number of input batches were about 24,000. And this is because 100 million records, if you split 100 million values into batches of 4096, you will get these many number of batches. So it was able to do an optimized scan of all the column values and reduce the job runtime. However, we have not gained anything on the number of rows materialized or the volume of data scanned. In order to do that, in Spark 3.2, which uses Parquet 1.11 under the hood, there is a concept of column index. Remember, we have column index, which stores the information at the page level, not at the row group level, but it has got more granular information that for each column page, what is the min, max, and count. And using Parquet tool, if we look at the user ID field, user ID column, we see that this is the column index for user ID, which is not ordered. While writing the Parquet files, which we did not sort the data frame on user ID, so the boundary order is unordered. And for each page, you see the minimum and maximum value of the user ID contained in that page. So now we can filter content not at the row group, but also at the page level. So we can be more selective into which page we want to scan. closely see our page min and max, because the boundary order is unordered, between min and max it's a very wide range. So again, it can happen that a certain column value can be present between the min and max of multiple pages, because the range is quite wide. So in order to further optimize, what we can do is we can create Parquet files in this example, which is sorted by the user ID. And once we do that, we see that now the column index for the user ID has boundary order of ascending, because we sorted while writing the Parquet file. And each page, if you see the min and max, they are quite narrow. So they have very tight difference between min and max. And now if you want to search for a specific value, you can be much more narrower in the search. And Parquet in fact can do this binary search to select pages which will match the value which we are looking for. Again, we can match for exact value, or we can match for a range of values as well. But the thing is, because now the order is ascending and the min and max of the page are not far apart, we can be much more selective into which pages to read for. And once we do that, when we try to run the same experiment on this file, which was sorted by the user ID, we saw that our bytes scanned became into kilobytes order. And now only 20,000 rows were materialized, because in this case only one page was scanned, and in our files every page had had maximum of 20,000 values. So only 20,000 rows were materialized, and the job took 2 seconds to complete. The other benefit is, because the user ID now was sorted, now Parquet can do smarter encodings to represent the data in the binary format, and that was evident from the size of the files. Now the size of the file was close to 240 megabytes. So instead of 560 megabytes, and remember, just to share, the actual CSV file which we used was close to 3 gigabytes. After storing them into Parquet, it was 560 megabytes. And then by using the ordering on the user ID, that further dropped to less than 250 megabytes. But what to choose as the column, as the ordering column, depends heavily on the use cases, because if you happen to order on one column, the ordering of the other column will be impacted. So try to optimize for most frequent use cases. You can choose your sorting column based on the type of workload you are dealing with, or the type of the query patterns you are using. And these are some of the numbers. Let's go through one by one. When it comes to the job runtime, with predicate pushdown, we see that the job runtime was 25 seconds. If we add vectorized scan on top of it, the job runtime decreased to 5 seconds. If we make use of column index, then the job runtime drops even further to 3 seconds. And if we have column index on the ordered column, that drops down to 2 seconds. So you see there is a strong savings in terms of job runtime. And a similar saving is there in the bytes scanned. So if you have in predicate pushdown, in our example, we ended up reading all the 560 megabytes. Vectorized scan does not filter out records. We ended up reading the same number of bytes. However, it was faster. But with column index, when we used the statistics of the page, that bytes scanned dropped to close to 5 megabytes. And this graph chart is on the log scale, so it is a couple of orders of magnitude of the savings. And if you have a column index on the ordered, and we are filtering on the ordered column, that drops even further to the level of kilobytes. And when it comes to the rows materialized, that also decreases from 100 million to a few thousand as we keep on adding these optimizations. And just to reiterate, these optimizations are there by default, so you probably won't need to tune it. You get all these functionalities and benefits by default without even having to worry about it. One more thing with optimization which is available by default happens to be dictionary filtering. So what happens is, as you remember, this is how the layout of a row group looks like. In a row group is made of column chunks, and inside each column chunk, if the column is dictionary encoded, the first page is the dictionary page followed by multiple data pages. In our situation, country was dictionary encoded because the cardinality of that country column was low, number of unique values were low. And what happens is, we can perform the filtering on their statistics at the row group, but this dictionary can also be consulted to further check whether a certain value is present or absent, because this dictionary contains all the unique values, and if a value which you are trying to search for doesn't happen to be in the dictionary, then you don't need to scan all the other data pages of that column chunk in the row group. So that's the idea of dictionary filtering, and it applies only when the column is dictionary encoded. So using Parquet CLI for one of the row groups, we see this is how the dictionary looks like. You see the value is the name of the country, and every value is assigned one integer index, which is used to encode the actual data. And if we enable this dictionary filtering and we try to search for a country which does not exist, first of all, we disable this dictionary filtering and we are trying to search for a country which does not exist. In this case, we ended up reading all the 560 bytes of data, and the job scanned through 2 files, materializing all the 100 million records, and it took 7 seconds. The same So dictionary filtering will help you a lot if the value which you are trying to search for does not exist, and if the column is dictionary encoded. But if the value which you are trying to search, it happens to be present, then you will have to read all the data pages as well. But again, it may be possible that different row groups for the same column, different row groups can have different dictionaries based on what are the unique values of the column in that row group. So you will be able to save if the dictionary content happens to be different across row groups. And one way to enforce this is by ordering your data set on this column. So if a lot of queries are running a filter condition on the country, you can choose the country to be one of the sorted column, just like what we did for user ID column a few slides back. Now, one more thing is, if you see that your all the unique values cannot fit into 1 megabytes of the dictionary page size, you can either increase the size of the dictionary page. We talked in the beginning about the configuration, or you can reduce the size of the row group, hoping that with reduced row group size, the number of unique values will also reduce and fit into 1 megabytes of dictionary page. Or you can do both. You can increase the dictionary size and reduce the column, the row group size as well. So what we found was that without dictionary encoding, the job runtime was 7 seconds, which dropped to 3 seconds. Without dictionary filtering, the job runtime was 7 seconds, and with dictionary filtering, it dropped down to 3. The rows materialized became 0 because we were looking for a column value which did not exist. And similarly, the bytes scanned was also 0 with dictionary filtering enabled. So these are the configurations which are enabled by default. And before we look into some of the configurations which are not enabled by default and which we can tune based on our use cases, let's look into a couple of points. First of all, based on the query patterns, you can create Parquet files which are sorted by the fields over which you are trying to do your filterings. And not only that, sorting also helps in joins as well. Like if you want to do this sort merge bucket map side join, then if the data is already sorted, and it also requires bucketing. But the thing is, sorting helps in joins and aggregations as well, because you have the contiguous values will belong to the same column value. And we should not whenever you are trying to make use of the row group statistics, try not to cast the field. For example, this filtering and this filtering may have the same effect finally. But in the second query, we are casting the user ID as a string. In the actual file, the user ID is stored as integer. So in the first case, we scan just a few kilobytes, like less than 1 megabytes of data. 20,000 records are materialized and 2 seconds of job runtime. Whereas in the second query, because we are doing casting and the actual content is integer, it ends up reading all the row groups across all the files, materializes all the 100 million rows, and the job runtime is more than 4 times higher. So unless you don't actually have a very good reason to cast it, don't cast it, because if you cast it, then the statistics of the row group may not actually benefit you. Now coming to the non-default optimizations, since Spark 3.3, not only filtering can be pushed down, rather aggregations can also be pushed down. So if you remember, the footer contains the information on the min, max, and count. So for a long time, we used the min, max values to filter out values if the value which you are trying to look for does not happen to fall in the min and max of the column. But because it already has the min and max, so if you happen to run a query which performs the maximum of a column value, why don't we take it from the statistics at the footer? And this is what the idea behind aggregate pushdown is. So the footer has got a statistics, and we can use those row group statistics for each column to answer aggregate queries for min, max, and count. So think of this example where we are trying to get the minimum, maximum, and count of user ID column. By default, what happens, it ends up reading a lot of bytes. More than 450 megabytes of data has been read. It materializes all the 100 million records. Job runs for 8 seconds. But once we enable the aggregate pushdown, and this aggregate pushdown works with only data source v2, so that is also one of the configuration we have to specify, and run the same query, we see that it reads just 17 kilobytes of data, and it just materializes 2 records, and the job runs for just 3 seconds. 2 records is there because you get the min and max for every file from all the row groups. So, and because you have got 2 files, it's just two max values which has to be aggregated. And this max, min, and count happens to be associative and commutative operations. So you can take the max of each file and do a global max to get the final result. So the job runtime reduces by about 3 times, from 8 seconds to 3 seconds. Rows materialized becomes very negligible as compared to without aggregate pushdown, and the same is the case with the bytes scanned. However, a few points to note about aggregate pushdown is that number one, it is supported for JDBC also. So if you want to do a maximum of a column and you are trying to read from a database via JDBC, these aggregations can be pushed down, because most of the times databases have a better way than Spark to tell you what is the min and max. And that is even further optimized if the database, for example, if you're trying to read MySQL and that database has got an index on the column you are trying to aggregate for min and max, then you can get strong benefits. Without aggregate pushdown, by default, what Spark does, it brings all the data from the database, materializes them into its internal row, and then calculates the min and max, which can be less efficient if your data volume is huge. But the problem is this aggregate pushdown is supported only for the v2 version of data source. So you will have to see that the format which you are trying to read has there is a data source v2. It has a data source in the second version. The first version of data source, which is also the data source v1, is less extensible than data source v2. And for most of the commonly used data sources like JDBC and ORC and Parquet, there exists a data source v2 implementation. And because this because the in case of Parquet, the statistics at the row group is used to answer the queries, only min, max, and count can be supported for aggregate push down, and that too not for all the column types, but only for Boolean, numeric, and date types. For the other types like binary, string, timestamp, and so on, this count aggregation is supported. But if you try to do a min and max, that won't benefit from the aggregate push down, either because the ordering is not well defined or because there is truncation. For example, if you have longer strings, then in order to keep the size of the footer in check, what Parquet does is it truncates the string and keeps only a fixed prefix in the min and max, which is not the accurate min and max if you are looking for that. So for a lot of and for int 96, that ordering is not very well defined, it's not as standardized. So because of multiple reasons, not all the types support min and max in the aggregate push down. And if you happen to apply filters over a column, and if that column is not a partitioned column, then also you won't be able to take advantage of aggregate push down, because as you know that aggregate push down takes the advantage of a statistics in the row group, and that statistics is across all the rows in that row group. So by any chance, if you happen to perform a filter operation which does not which eliminates some of the rows in the row group, then the min and max of the row group may not apply to the data set you are scanning. So you can filter out files if you are trying to look into specific directories, and those directories or subdirectories are specified by the partition column. So if you have a filter condition on the partition column, then you know which directories to go into, and and then once you go into the directories, you know, like, okay, which are the files and what are their statistics or in the footer. But if you, and that is fine. So if you have a filtering on the partition column, that can take advantage of aggregate push down. But if you have a filtering on the non-partitioned column, then the statistics of the row group may not apply to the result set you are looking for. And in that situation, the aggregate push down won't be applied internally. And same applies for grouping also. So if you are trying to do a min and max group by certain column, then unless that column is a partitioned column, aggregate push down won't be applied. And right now there is, and again, one more thing about that is there are some talks happening like, okay, if a certain row group can be eliminated completely, we may use aggregate push down. So that, or it can take advantage of page level statistics as well, so that it can be more smarter. But right now, if you are trying to filter out the content inside any file, then the aggregate push down is not applied. And the other limitation right now is this aggregate push down happens only for simple aggregates like min, max, and count. If you happen to have nested fields, or if you have subqueries inside the min and max, that is not supported at the moment. Now the other room for optimization is the compression algorithms. There are a lot of compression algorithms which are supported, and the flexibility or the liberty of using compression or codec has been there since early release of Spark. And quite recently in Spark, since Spark 2.3, ZS standard has also been added, which happens to be one of the modern compression algorithm. And so first of all, the default compression algorithm in Spark, whenever you are writing Parquet files, happens to be snappy, which is optimized for speed. It is fast, but it may not give you a very good compression. It is based on dictionary compression of LZ77, and then there is gzip, which is optimized for space. It can be slower than Snappy, but it will give you a higher compression. It is also based on LZ77 dictionary encoding, plus it also uses Huffman encoding. We won't go into much detail, but if you just happen to be curious, LZ77 dictionary compression, what it does is it checks the repeated sequences and replaces them by back references. In Huffman coding, it uses a prefix tree so that frequently used symbols are mapped to a shorter bit sequence. And then there is a modern compression Z standard developed by Facebook, and this has Snappy-like speed as well as gzip-like compression. So it takes like kind of, now you don't have a trade-off. You can get higher speed and a better compression at the same time. It also uses dictionary compression of LZ77, but it uses finite state entropy, where the symbols are encoded into a single state. So it all goes back to arithmetic coding and arithmetic numeral systems, where in the modern systems you have range-based numeral systems, where we won't go into more details, but the key takeaway is Z standard is something which you would like to try out, and this Z standard has seen evolution. When it was introduced in Spark version 2.3, it was not very fast, but it has a lot of optimizations have been gone into choosing the buffer, doing a garbage collection, and now it has reached to a point where it is much more mature than ever before. And this is something you can try. So what we did is, and how can you specify is very simple. You specify the compression codec configuration. The compression codec can be none, uncompressed, Snappy, which is default, gzip, LZO, Broadly, LZ4, Z standard. So these are the different compression codecs which are supported. And what we did is we tried to evaluate some of the compression codecs, and we tried to see what is the output file size and how much time did it take to create and save the file into a storage, and then how much time did it take to decode or deserialize the file and read the file to do some column aggregation. And this is the result we found. We saw that our actual file size of the CSV was close to 3 gigabytes. With Snappy and LZ4, we were able to bring it to close to 1 gigabytes, which is a strong benefit. But with gzip, we were able to bring it down even further. And with Z standard, you see it has got similar compression as of gzip. And Z standard and gzip, both of them have different compression levels. So gzip has got compression level 1 to 9. 9 means slowest but highest compression, and 1 means fastest but low compression. And Z standard also has compression levels from 1 to 22, and it has a similar meaning that 22 means slowest but highest compression, and level 1 means fastest but smallest compression. The default compression of Z standard is 3 in Parquet with Spark. However, with Z standard level 1, we see that which happens to be the fastest, the size of the file was much smaller than Snappy or LZ4. And how much time did it take to write those files? So once we looked into that, we saw that CSV, it was taking about more than 75 seconds. Snappy took a bit less, gzip took the highest, whereas Z standard took similar time as of Snappy. With Z standard level 1, it took the smallest amount of time to save the file. And if you see, Z standard level 1 also has a very strong compression, not as good as gzip or level 3, but better than Snappy and LZ4. So you can in fact have a job runtime or the file save time smaller than Snappy, but achieve a compression more than Snappy as well. For most of the practical purpose, the default level, which happens to be the level 3, is also fine. And when it comes to reading the files, then different compression algorithms were very, very similar. All of them took around 10 seconds of time to do a column aggregation. So not much of a difference over there. And This compression can be applied not only to the output files, but it can also be applied to the event logs. So event logs are disabled by default, but you can enable it, in which case all the metrics from the executors are saved to a file. You can compress that file as well. And we can compress the temporary files, the shuffle files, the broadcast variables as well. So you can choose different compression codecs for all these three different of all these three classes of information. And based on the version of a Spark and the choice of your compression codec, you can also choose compression levels. For example, you can choose a compression level for gzip or for ZS standard, but that is supported in Spark 3.5.x and onwards. Now, the last thing which we are going to talk about is the bloom filters, which is supported since Spark 3.2, and it also uses a Parquet 1.11. So bloom filter are probabilistic data structures, as we talked about in the beginning. And what we can do is, not only based on the statistics at the row group level, we can also use the bloom filters, which can be defined at the column level, to skip reading a certain row group if the column value which we are trying to look for is definitely absent. So bloom filter gives you two responses. If the value which you are trying to look for, it can be present, which is it may be present, or it is definitely absent. So if the value is definitely absent, you can just skip reading that row group. And when you are creating a file, you can enable the bloom filter when you are trying to write a file. By default, it is not enabled. So in our example, when we had 100 million records and we had we created two files, and both of the files were 280 megabytes. And what we saw that once we created the bloom filter on the user ID, we found that, and using the Parquet CLI, we can also inspect whether a certain value, what does the bloom filter return for a certain column, for a certain value. So we looked into one of the files and we checked like whether the value 1 is present or not, whether a high value is present or not, and whether this is one of the existing values, whether it is present or not. So we were trying to look into whether, what does the bloom filter say? And if you see, the bloom filter says for all the values that it can be present. Now, situations like this is of no benefit, because if the bloom filter says you that the value may be present, then you will have to read that row group. And if the bloom filter says that the value can be present for all the different types of values, then it is of no use. In fact, it is suboptimal, because now you are scanning the row groups, but you are also scanning the bloom filter. So the idea behind bloom filter, the benefit of bloom filter is that your data volume which gets finally scanned should reduce. What was the reason? The biggest reason was that we were using the default size of the bloom filter, which is 1 megabytes. And one takeaway is, if you have got 1 million unique values and you would tolerate 1% of false positive, then you should have a bloom filter of size approximately 1.2 megabytes. Now in our situation, with 100 million close to 100 million unique values for the user ID, and as we have seen before as well, our row groups were having 22.7 million unique user IDs. Sorry. So our row groups were having 22.7 million unique row user IDs, and in that setup, 1 megabyte of bloom filter is too low, and it will give you a lot of false positives. So by doing that calculation, we will need somewhere around 26 or 27 megabytes for the bloom filter. And because the bloom filter size should be a power of 2, the nearest power of 2 is 32 megabytes. So what we did is we used 32 megabytes for the bloom filter. So tuning the bloom filter, we used 32 megabytes as the max size, and we enabled it to be adaptive, because we don't want to give the number of distinct values, because that can change over time. So either you can give the expected number of distinct values for that column, or you can just give the maximum bytes and enable the adaptive bloom filter. So after this, we created new files where the size of Bloom filter was 32 megabytes. And now if you try to search for values, the Bloom filter is much more accurate than before, and it will tell you that, hey, value 1 is not present. Value which is a high value, this is also not present. But this value can be present. And even if it can be present, it is not present across all the row groups. As you see, for the row group 0, this value can be present, but for the other row groups, this value is definitely not present. So for our use case, we use this 32 megabytes of Bloom filter, and that looks much promising than before. However, Bloom filters have a downside that they will increase the size of your Parquet files. Now think of this example where you are using 32 megabytes for the Bloom filter or only for the user ID column. And if you have 3 row groups, then there will be additional 96 megabytes of Bloom filter for every Parquet file. And if you have 2 Parquet files, then you just multiply it by 2. And that is also evident from the file sizes. As you see that our original CSV was 2.2 gigabytes. Okay, so I will correct myself. In the beginning, I said that our CSV was 3 gigabytes. Rather, it was close to 2 gigabytes. So sorry for that. So our original CSV file was 2.2 gigabytes. And once we do ZS standard compression, we have 566 megabytes. So this is the file we have been talking about so long, that we have 2 files, and both the files were approximately 280 megabytes because they were compressed using ZS standard. And if you go by default of 1 megabytes of Bloom filter, then that file, then that directory will be 572 megabytes. And that is quite reasonable because we have 2 files and each file has got 3 row groups, and for each row group we have got 1 megabytes of Bloom filter. So for 2 files, 6 row groups, there is a difference of 6 megabytes. But now if you use a Bloom filter of 32 megabytes, the file size will again increase based on the size of the Bloom filter. But having said that, again, you see there is the final size of the Parquet files is much lower by a factor of 3 as compared to the original CSV file. And in this situation, we were enabling we had the Bloom filter only on the user ID, so you can choose on which columns you can have Bloom filter. Because if you have, let's say, hundreds of columns, then if every Bloom filter takes a certain size, then the total size of the file simply expands. Okay, so going ahead, let's look into the impact of the Bloom filter. Let's say the Bloom filter, when reading, we disable the Bloom filter, and we are trying to we are trying to filter out the Parquet files for a user ID. And I looked into the metadata. This is the user ID which is present across all the page range and as well as all the row group range, like all the column statistics which is stored at the row group level and at the page level. This is the user ID which will match all the pages and all the row groups. So essentially it will do a full scan of all the row groups across both the files. And we are not using this sorted on the user ID, just in this part of the experiment. So once we do that, it scans all the 560 megabytes of data, all the 100 million records are materialized. It took 7 seconds. But if we enable the Bloom filter on the same and we try to search for this user ID, as you can see that the volume of data which gets scanned becomes much less than 560 megabytes. Now it is close to 300 megabytes. The rows which got materialized was 22.7 million, so savings over there as well. However, the job runtime did not change. So we were able to save on the bytes scanned, and we were also able to save the number of rows which got materialized. So if this scales to a larger volume of data where you have data in terabytes or petabytes, you might be able to see appreciable difference. But for our few hundred megabytes of data, we did not see real difference in the job runtime. However, However, if the record is absent, if the value which you are trying to search for does not happen to be present across any of the row groups, this is where the Bloom filter shines the most. If we disable the Bloom filter and run the experiment for a user ID which does not exist, we end up scanning all the data, materializing all the rows. It took 7 seconds, very similar to as before. But when the Bloom filter is enabled, we see that the bytes scanned becomes less than 200 MB. There was no record materialized because by scanning the Parquet, all the row groups were skipped, and it took just 2 seconds. Now, if you are wondering from where does this value of close to 200 megabytes come, this is because the Bloom filter has to be scanned. And we looked into so this is how the variation in the job runtime looks like. From 7 seconds, it drops to 2 seconds. We have bytes scanned, which is now close to 200 megabytes. This is because we have 96 megabytes of Bloom filters in one file. So if you multiply by 2, that's the number of 192 megabytes. And that is the only data which is scanned. All the row groups were skipped because the Bloom filters said that the value you are looking for definitely is not present. It is absent in all the row groups. And there were no records materialized because there was no row groups scanned at all. So a few points about Bloom filters. Bloom filters are there for every row group. You can also set it for specific columns. You have to specify the expected number of distinct values, or you can use adaptive Bloom filter, and you can just tell the maximum size of the row group of the column value. Oh, no, sorry. Or you can choose the adaptive Bloom filter and set the maximum size of the Bloom filter per row group. The default maximum size of Bloom filter is 1 megabytes, which can be ineffective if the columns have high cardinality. So as a rule of thumb, in order to achieve 1% of false positive over 1 million unique entries, consider a Bloom filter of around 1.2 megabytes of size. And at certain point of time, if the size of the Bloom filters becomes comparable to the size of the row group, then it is not worthwhile to having a Bloom filter at all. Now remember, as you know, the Bloom filter is there for every row group, and you have to scan the Bloom filter to either consider the row group for scanning or skip the row group for scanning. If the size of row group is 128 megabytes, and if the size of Bloom filter is also 128 megabytes, then you won't see any space in the benefits of bytes scanned, even if you have Bloom filter. So if you have and in fact, the bytes scanned can increase as well in such a situation. So the Bloom filters should be a cheap way of discarding row group while scanning. So if your so think of a situation, your Bloom filter happens to be 128 megabytes, and your row group also happens to be 128 megabytes. If you enable the Bloom filter, you will have to read the Bloom filter for sure. So 128 megabytes will be scanned. And based on that, if the Bloom filter says, yes, the value can be present, you will have to additionally read 128 megabytes for the row group. If the Bloom filter says no, then you will skip reading it. But the thing is, even if you do not have Bloom filter, so basically you are reading at least 128 megabytes. That's the least. Now, even if you don't have Bloom filter in those situations, you are sure to read 128 megabytes. There is no way of skipping based on the probabilistic value. Then it's the same. In fact, it's quite predictable, and Bloom filters in those situations can incur more bytes scanned. So the thing is, if the size of the Bloom filter becomes comparable to the size of the row group, then you can think of any other way of better partitioning your data, or sorting your data and take advantage of column indexes, or maybe try exploring the possibility of dictionary encoding or dictionary filtering. And Bloom filter is not a best choice for that situation. And Bloom filters have another disadvantage or limitation, that they are suited only for the point queries. So if you're looking for an exact value of a column, then you can get maybe yes or no as a result from the Bloom filter. But if you are trying to search for a user ID between 100 and 200, that kind of range queries, those can't be answered by the Bloom filter. And most of the savings happen if the Bloom filter says no, which means that the record is the column value you are trying to search for is definitely absent. In which situation you simply skip the row group. So we have seen that in Parquet file format, you can filter on the row group level statistics. You can take advantage of the dictionary values to read just the dictionary page, and if the page says this value is not present in the column chunk, then you just skip that column chunk or skip that row group. And you can also have index on the page level. You can take advantage of the column index to skip certain pages. And then there are Bloom filters. If the column has got high cardinality and it is not ordered, where you means the column has high cardinality means dictionary encoding is not possible, and it is not ordered, which means column indexes can't be efficiently used, then of course Bloom filter is a way to further optimize or make your reads efficient. So this brings us to the conclusion. Hopefully we were able to cover all the things we had promised in the beginning, that Parquet with Spark is popular, and over a period over the last many years they have been evolving. There are a lot of configurations and knobs to tune to make the most out of it. A lot of optimizations are there by default, which includes predicate push down, which takes advantage of the statistics at the row group level or at the page level. Basically the number of rows which gets materialized by the Spark is less, because just by scanning the Parquet file at the Parquet level itself, you get the efficient filtering. Column pruning is basically one of the is possible, because if your Parquet file has got 50 columns and you are trying to read just 2 or 3 columns, then you don't have to scan all the rows or all the column chunks. You just scan only those column chunks which your query is looking for. Dictionary filtering is possible if your column values have lower cardinality, and all the unique values can fit into a dictionary page, which happens to be the first page in the column chunk. And column indexes can be used where the statistics at every individual page level of the column is stored. And not only, even if you happen to scan a row group or a column chunk, you have the choice of skipping certain column pages while scanning. And then there are a bunch of optimizations which we can tune. We can choose the size of the dictionary page, which is 1 MB by default. We can choose the size of the column page, which is also 1 MB by default. And one point to note over here is, if you happen to choose a higher value for the data page, chances are that you can benefit a little bit better from the compression. But which also means that the smallest level or the smallest quanta of bytes scanned will be then controlled by the size of the page. So even if you have column index, if you happen to select a page, you will have to read the content of that page. You will have to scan the content of that page. So higher size of the page means the lowest value which you can scan also increases. We can also tune the size of the row group, which happens to be 128 megabytes by default. And with vectorized reading, we can specify how many column values would we like to read in a single shot, which happens to be 4096 by default. We can use a compression codec different from the default of Snappy. ZS standard is quite promising, something we can try out. We can push down aggregations. Again, not in all cases, but in a lot of cases, not only with Parquet file, but with the JDBC source as well. And even if you are using for Parquet file, a lot of different data types can be, we can take advantage of aggregation push down with different data types. The data types can be integer or numeric values. It can be dates, Boolean values, and so on. And then Bloom filters are there for us in the recent releases of Parquet and Spark, where we can further take smarter filtering on the column values. These are some of the references if you want to go deeper into the things like the Parquet format. There are some blogs, some tech talks, research paper on Dremel, some benchmarks. In case you are interested, these are the slide. These are the links, hopefully, which will help you. So thank you so much. If you have stayed till so far, I hope it was a good use of your time, and thank you so much for the attention you have given to the video.